All right, so we should have our second midterm here a week from today. That'd be the 20th. And that would cover the chapter on flow rate and velocity, which is 9. And then it would cover the Bernoulli's equation stuff, which is 10. And then the head loss stuff, which is 11. And then also a little bit on the minor loss stuff, which is 12. And then that network stuff, which is 13. Okay. So 9, 10, 11, 12, 13. I'll get you a review sheet on this one Wednesday. Okay. So that's kind of what's up. So that'll be Monday. All right, why don't we see, there is that stuff due today, but let's just have a quick look at it here. See if there's any questions. Are there any questions on the first ones, 11, 2, 3, 4? Those are basically just reading the chart is what those are about. So 2, 3, 4, 6, 7, 2, 3, 4, 6, 7. And 10. So we good on 2, 3, 4? Good to go. All right.
Do you have any more of the packets with the 6 problems?
I think I might have enough. Anybody else need one? All right, so 2, 3, 4, then we got 6 and 7. Okay. 6 and 7, we good on that? Okay. And then 9 and 10, when C is not 100, you all good on using that equivalent flow? So when you go to those charts, you got to use the equivalent flow. So that's kind of how I remember that. When I'm on the chart, I'm using the equivalent flow. So when I take a number to the charts, I've got to convert the flow into the equivalent flow. When I take a number off the charts and do something with it, I've got to convert that back to the actual. I want to find an actual flow. Okay. That's kind of how I think about that. Okay, so we got that. Let's see. How about that handout? Are there questions on that? Are we doing okay with the handout? So the first two on the handout were just to find the pressure. So we're doing okay with those. You got the answers there in Moodle. So we'll find the pressure in the hydrant on the first two. You okay with those? Well, actually the hydrant on the first one, then point B on the second. And then the next two, we got C of 100, and we want to find the flow on the first one. And then we want to find the pipe size on the second. So that's for C100. When you want to find pipe size, what you want to do is find one pipe that's too big, the other pipe that's too small. So find a head loss high and low. Term for that is bracketing. Okay. And then you use the bigger pipe. It's safer to use the bigger pipe, right? Okay. So once you get the head loss bracketed, so to speak, then you use the bigger pipe, okay? And then are y'all okay with the last two where C is not 100? Those are a little bit trickier. You just got to remember to use the equivalent flow. Y'all okay on those? Questions on those? So those are due today.
We also have 12.1 and 13.1.
They'll do Wednesday.
Oh.
Okay. So on Wednesday, what I'll do, I'll get all your homework back to you. I'll get you an update of where you are in the class too, and then we'll and a test review too. Okay. All right. So 12.1 and 2. Well, actually, it was only 12.2 because we already did 12.1 in class. All right. So everybody good on 12.2, getting the head loss for that? Yeah.
Question.
Uh-huh.
Do you not add up all the different head losses for all of the different sections?
There's different ways to do it. You can come up with a total length.
Because I did a head loss on each of them, and then I added it all up, and it was like 32 feet.
What did I get?
I think it was way lower. It was like 1.7. I think I'm missing something. Is it per 100?
Okay, now what you do on 12.2 is you add up the equivalent lengths, which is 32.
Okay.
Then you add that to the lengths of the pipes.
Isn't that what the length of the pipes is?
No, mine was 32 when I added up the equivalent lengths. I remember, let's see. Yeah, I know. Okay, so are we good on that? Now this is for Wednesday, 12.2. Are we okay with that? That's a minor loss problem. Just kind of keep track of what you're doing with that. You're going to find L over D for the 3 fittings, and then get the equivalent lengths for the 3 fittings, and then you'll find the head loss. So, I mean, there's different ways to do this, and to add them up. But what I do on this, find, and you kind of do it in a flow chart almost. So we're going to have an ordinary inlet, and then we've got a standard elbow. This is 12.2, and then we got an open gate valve. Okay, so what you want to do is find L over D, then take L over D times the diameter. Remember to get that in feet and get the equivalent length, and then find the head loss. Well, actually what I do, I get these equivalent lengths first. And I get 6.67, and then I get 21.33, and then I get 4 flats. And then I add those up. I get 32, and then I take 32 plus these other 2 lengths. And then I get my total length, and that's 66, I think. Yeah, 66. Then I find the head loss for 66 feet of pipe. That's how I do it. There's other ways you can combine things, There's 1.70 feet. Okay. So that's how I would approach this one. Like I say, there's different ways to do it. Okay. We good on that? So that's how I would approach that one. And we already did 12.1, so you can have a look at it. It's the same process, you know,
Right.
that'll help kind of walk you through it, okay? All right? We're doing all right? So head loss for 66 feet of pipe is what you'd find, and that's 1.70 feet. Okay. Good on that. Okay. And then the other one is this one. So what you want to do, you know, you got 1,600 gallons per minute flowing in and flowing out. Just take a guess on how that flow splits. I mean, what you know is the sum of the two flows you're using have to equal 1,600. Okay, so you know that, you know, column Q1 and Q2, you know that Q1 plus Q2 has to equal 1,600. And you know that the head loss for Q1 has to equal the head loss for Q2. So guess and check is basically how you do these.
Head loss is going to be close or like
Don't. If you're within, if you're close, you're good. If you're, I don't know.
old numbers of flow.
Yeah, there we go. That's probably best. Yeah, if you round your head loss to the nearest even foot, you know, that should be good enough when you're doing this. You know, we don't need to spend forever on it. Just get the basic idea, okay? And you know, this is a little bit of a process when they do this for real. For what we're doing, we don't want to overkill it. I just want you to have the idea, you know, the basic concept of it. You're running head losses different directions, and they should all equal out, and the flow equalizes to get equal head losses. Have y'all done tech electricity yet?
Next term.
Next term, okay. Well, you'll probably do some of this with current too. That's how you figure out how current flows through circuits.
So if you were to work backwards, it would help you find like what size pipe you would need on the other side of a.
Yeah, you could do different things with this.
It was going to equal out either way,
Right.
right? It was going to equal out.
If you put a bigger pipe in, obviously you get more flow going through there because it's going to take more flow to get that head loss. So this is basically how they analyze those big systems, you know, like what you got in this city. Okay. All right. So I'll get you a review on Wednesday. You know, we can go over it on Friday. Okay. All right. All right. All right, why don't we continue on with pumps here a little bit? We got a good bit of time, so let's use it to keep going over pumps. This is something you want to have a good understanding of by the time we're done here. Remember, next week we got a short week, so remember that.
Talking about it, we have class Wednesday?
Yeah.
Okay. I didn't know.
It's a good question. It's
no, it's a good question. I was supposed to.
It is kind of a slippery slope because eventually you'd end up taking the whole week off.
I mean, that's totally fine. We can take our mission and call it good, right?
You'd be okay with it? You'd check it off. You'd sign off on it.
Might be here doesn't mean we're gonna be here.
Yeah, I know. I'll record it on Wednesday too. You know, we'll keep going. I'll make a recording. So let's have a look at pumps here. Okay, now pumps can be set up in different ways. They can set them up in parallel and in series, both. Okay. On page 134. Okay, now those of you that Might have been working this past summer. Have you all seen a duplex pumping station?
For like a duplex?
That's pretty good. Yeah, I never heard that one
You know
before.
what? I had the same question.
Yeah. All right, here's a duplex system. Now, what we got here, we got the power coming down to these pumps. See the outlet pipes coming here and elbowing up? They've cut them. They don't show the rest of the outlet pipe because they probably because they just mess up the diagram too much. Okay. And it just cluttered up too much. But there's actually outlet pipes coming from each of these pumps. So what we have here for a duplex pump, duplex just means two. We've got a wet well. These are submersible pumps. Y'all, okay. Okay, so they're pumps that go underwater. They're sealed, obviously, so that the electronics can function in them. Okay, so what's going on here? We're going to have water flowing into this tank here, this wet well, as you call it. The water will start coming up. Here are a series of switches. In the old days, these were float switches. It's changing more to they're more like electronic switches, but however the heck they work, here's how this would go. Switch number, this one right here, number 7, when the water in the wet well rises to that level, this switch is going to turn one pump on, okay? Now, hopefully that pump can keep up, and it's designed so it can keep up. So it'll push the water out of the pump station through this pipe, which keeps going, and will go to wherever this pump station is going. But let's say it can't. So even though the water's hit this level, pump number 1 cannot keep up. There's a second switch up above. If the water keeps rising and hits the second switch, pump number 2 will come on. So now you've got both pumps going. Okay? Now what do you suppose switch number 3 up here is for?
Alarm.
Yeah.
Public works.
Which I wouldn't call it public works. I would substitute the pronoun me for that for most of you guys. All right. Because if both pumps can't keep up, you've got an alarm switch up here too. And if the water keeps rising, you're going to get a signal somewhere that says Houston, you have a problem, and you got to get out there and try and do something about it. And probably a roaring rainstorm or something like that is probably how that's going to go. Okay, so that's a duplex system, and this bottom switch is to do what? Shut it off. Yeah, as the level drops, you don't want to run the pumps dry, so you shut it off before it hits bottom. Okay, so that's a duplex system. All right, so theoretically speaking, in a duplex system. What's going to happen here, and let's go back here for just a second. There we go. So that's from Federal Pumps. Might be up in, I don't know where they're from. Anybody know Federal Pumps? I don't either. Nice schematic though. It's a nice job. Okay. All right. That's a duplex system. Okay. Now, what we do if we draw a real simple schematic of that, we put them in parallel, okay? Pumps in parallel. So what pumps in parallel do is they will double the flow theoretically. Okay, the flow will double, but the pressure will stay the same. Okay, so in a parallel system, you get twice the flow but the same pressure. That's the intent of a duplex system. Now, truth be told, when you start looking at all the head loss you build up in that pipe as you push the flow out, because eventually those two pipes will merge into one, you're not going to theoretically you'll double the flow, but in truth you won't, because you'll have so much head loss trying to push a huge flow through one pipe. You're not going to get a true doubling of the flow. Yeah, but theoretically you do. All right, now the other setup for pumps is in series. And that's kind of best shown perhaps by a multi-stage pump, which here's a multi-stage pump. What you have here are multiple impellers in the pump. This is kind of hard to see. I think it's 3. What you've got are just multiple impellers in there. So the flow will hit the first impeller, get pressurized to get push to the second where it'll get more pressurized, push to the third, et cetera, okay? So notice we got essentially one pipe, one pathway for the water, but we're running it through multiple impellers. So if you set up your pumps that way, what you're getting is a series pump. They're in series, okay, one after the other. The flow stays the same, but the pressure will double or triple or quadruple or whatever, okay, depending on how many impellers you've got. So what you need there is a real big motor to turn all those impellers, okay? So that's the setup that you can have on pumps. And typically, from my admittedly limited experience, parallel pumps are duplex lift stations, usually for sewage. Can be for storm water too these days. Okay, and you've got a wet well, 2 submersible pumps, a primary and then a backup. Now, of course, the switching will switch primary and backup back and forth all the time, so you don't wear one pump out and never run the other. So they'll switch what's first and second. But that's basically what that is. Okay, and then series pumps are just multi-stage pumps, which are high pressure pumps. Is their intention to push the water a long way. Okay. We good on that? A little bit of terminology here. Okay. Now the pump is here. You've got the high pressure side and the low pressure side. There's lots of different words for that. High pressure is also discharge and outlet. Okay. Low pressure is the suction side or the inlet side. So what a pump is doing is it's introducing pressure head, and it's pushing the water from one reservoir to the other. Okay. Now you can set pumps up in 2 different ways. One way is you lift the water out of the reservoir. And one of these summers, I got to remember to take a picture of one of these. What you get is if you ever, I know a lot of people here do float trips, a float trip down the Willamette or Santiam or something like that. And sometimes when you look up on the bank, you can hear these pumps too. If here's the river, a farmer will have a pump up here, a motor, you'll see the pump motor usually. And then they've got the pump itself, and then they've got a pipe going down into the river. They lift the water up out of the river to the pump, and then they push it into the field. You all seen those? Okay, that's a static lift, because they're lifting the water out of the river to the pump. Okay? Now, that's one way you can set up a pump system. The other way you can do it is have the suction side reservoir here, okay, above the pump. Now that's kind of nice because that pushes the water into the pump. You don't have to lift the water into the pump. That's called static head because you've got positive head, you've got gravity pushing your water into the pump. That's like a submersible pump is what that's like, a pump that's underwater, which is one of the downsides of that is you have to deal with the fact that water is above your pump. You might have to have a submersible pump or something like that. Okay. All right, now, one of the primary things that pumps do, remember, they lift water and they also make it flow. So one of the primary things we got to do here is lift the water. So if you have static lift, you've got the suction lift to get the water from the reservoir to the pump, and then the pump will push the water up to the outlet reservoir. If you add the two, the static suction lift and the static discharge head, as they're called, you get the total static head. That's the total distance you've got to lift the water. That's on page 136. Okay. Now, lifting water is difficult to do. What you do when you lift water is you create a vacuum in the volute. There's a vacuum here. Usually not a complete vacuum, but as good a vacuum as you can get. That's caused by the spinning impeller in the volute. As that thing spins, it basically throws all the air out of the volute and you get a vacuum there. So, being as there's a vacuum there, the pressure is about equal to 0 in the volute. Okay. So what you've got is you've got the atmospheric pressure pushing here. And what that does is it pushes the water up the piping into the volute. So the term lifting water is really kind of a, well, lifting water is okay, but sucking water is not really what's happening. What you're doing, you create a vacuum, and the atmospheric pressure pushes the water into the vacuum. Yeah, like a straw, like many, yeah, that's the most common example. Okay. So, how high can you lift the water then? Yeah, there's different numbers that you could use for that. See, if you've got 0 pressure in the pump, and what's the average atmospheric pressure? 14.7. You've got 14.7 psi to work with. And we got what, 2.31 feet per psi. So theoretically speaking, that's 34 feet. You can't lift water any higher than 34 feet on average. You just can't do it because you're not, all you're doing with a pump is creating a vacuum. That's all you can do. Okay? So you can't lift water any higher than 34 feet. You can push water more than 34 feet, but you can't lift it. It doesn't matter what you do.
No, I mean, if you had 134 feet, then you have to get another pump for that, and then lift it again.
Well, really, you'd be more pushing the water with the first pump. That would be the right way to word that, I think. Yeah.
That also included its prime.
Yeah, it has to be primed, to work properly. But, it's 34 feet. That's, yeah, if you had if you're going above your first impeller, you could go much higher, yeah, right. But just flat lifting, with just a pipe stuck in the water, 34 feet's it, okay. Now, practically speaking, you're probably about 20 to 25 feet, okay. So 34 feet is the theoretical maximum. (20 to 25 feet is the practical limit. Okay. Now you can push water as far as you want, but you can't lift it any higher than 34 feet maximum and 20 to 25 feet in a practical sense. Okay. So keep that in mind about these static lift pumps. And now you can get into trouble if you try and lift too high. You can get into what's called cavitation, which we'll talk about a little bit later. But you could have a lot of trouble in your volute if you're trying to lift water too high. Or if you have too much head loss on the suction side. So minimize the fittings, minimize the valves and everything on the suction side. Put them on the discharge side. That's the basic idea there. Okay, so that's static lift. So, okay, now static head, gravity causes the water to flow into the volute. So with a static head pump, you don't have as many problems as you might with a static lift pump. Okay, now if you want to calculate some of these numbers, you just need to know the elevations where things are set. Okay, so this first pump, how high are we lifting here? Yeah, looks like about 7 feet. And then the discharge, what do we got? Okay. Okay, so you're lifting water 7 feet. The discharge head is 118 feet. The sum of them is 125. So what's happening here, this drawing isn't to scale, but that's 125 feet. No, it's not, it's 118. That's 7. So the total is 125. Okay. So that pump has to, in the end, push the water 125 feet. Okay. Good with that? Good. Okay, how about this one? Yeah, 20 feet of lift, or 20 feet of head to get from the inlet reservoir to the pump. That's actually got 20 feet of positive head there. And then we've got, 678 minus 622. And that is, 56. So the total lift is the difference. This time it's 36 feet. You could either take 378 minus 642, or you could take 56 minus 20. Either one will get you the same number. Okay. The idea here is if there weren't any pump there, if that was just piping, what would happen is the water would seek its own level over here, and you'd get 36 feet of lift. See, the pump isn't required to get the water over here. It'll just flow there on its own. 36 more feet will get you up to 678. That's the idea. Okay. So when we start looking at what pumps do, they lift water. Okay.
In that situation, wouldn't it be better just to cut out the pump and just take the top of the water from one side and the top of the water from the other? And do one, the higher one, and the lower one?
That's essentially, well, let's see, as far as how this pump works, this is getting what you call positive head coming in. So this could be like a submersible pump, which might just be a matter of what you need to do before you pump the water. Quite often you have like a wet well or something that collects water, like I was just showing you earlier, which is why you got that positive head coming in.
I was just looking at it, thinking, why do I need to do the calculation for
for
when I
this
went
to
to the
count?
pump?
Okay.
Just cut the pump out all the way,
Yeah.
and just take one and do the other, and you already had it.
Right, yeah, it's true. The easiest way to look at it is this. These two numbers aren't that particularly important in this case, okay? Sometimes you want to do some calculations to figure out what's happening in the pump itself. When you've got static head, though, it's usually not a big issue. You don't need to worry about that so much. So yeah, it's probably easiest just to subtract the two elevations. Okay. All right, now if we want to know how pumps are working, on page 138 here, what you really want is dynamic head. See, what we're looking at here is how to size pumps. Get the right size pump to do the job you want it to do. Remember, what pumps do is they create pressure or head, and they also create flow, is what they do, all right? So if you just have static head, that's pretty easy to calculate. Those are just elevation differences. Static means no flow. Dynamic head occurs when the water starts to flow through the system and you get head loss or friction loss. Okay, so dynamic head is what you really look at when you size the pump, because the pump not only has to create pressure or head, it also has to pump at a certain flow rate to move the water through the system. And when that happens, you get friction loss. So if we really want to size the pump for what it's going to do, we got to know the flow rate, and from that get the friction loss. So you take the friction loss, add it to the elevation head that we were just looking at, and that'll get you the total, what's called dynamic head, which means the water's flowing, it's moving. Okay? And that's what the pump has to do to get the water to flow from one reservoir to the other. So why don't we have a look at this thing on page 139, if we got time to do one of these. All right, and let's just kind of go through and figure this thing out. Let's see if we can find what we call the TDH, total dynamic head, for this thing. All right. All right, so on page 139, what's the total static head for this one? Yeah, it's the one we were looking at earlier. Take the difference in elevations and you get 36 feet. That's how high the water has to be lifted. Okay, but then we've got some fittings, okay, that we have to consider. And then the next thing let's look at is the length of the pipe itself. And is this matching what you've got in your book? I've changed this around a few times. So yeah, total length of pipe. So how long is the pipe we got to push the water through?
186.
186? Yeah, looks good. 26 and 160. Everyone picking that up okay? So we got to push the water through 26 and 160 feet of pipe. Okay. Now let's find the head loss per 100. We got 1,300 gallons per minute and 8-inch pipe. So what's the head loss per 100 on that going to be? Yeah, 4.85 feet. So that's the head loss per 100 feet of pipe. Oh, is it?
Well, on ours it was. I don't know.
Okay. That's a pretty easy one then. All right, so what we want to do next is we want to figure out what the equivalent length of the fittings are, okay? So for starters, we've got 8-inch pipe, which is 8/12 of a foot, 0.667 feet. That's the pipe diameter. And what we want to do then is get those L over D values, which I think I show. So what? We've got two elbows. They've got an L over D of 64. You just find that on your minor loss chart. And that's times 0.667. All right. So that comes out to be, I think it's 85.3. We're good with that? So what that says is those two elbows will have the same head loss as 85.3 feet of pipe. That's what that means. Okay. So I'm taking the number off the chart, 64. I got two of them, so I multiply it by 2, and then I multiply that by the equivalent, by the diameter of the pipe in feet. Okay. And then I got an ordinary outlet, which is 20 times 0.667. That's 13.3. And then I've got an inlet, which is 30 times 0.667, and that's 20 feet. So I can add all those up, and I'll get 118.6 feet. Okay. So that's the equivalent length of all those fittings. They have the same head loss as 118.6 feet of pipe. Okay. We're good with that? I'm just getting the equivalent length of the L over D value for the fittings, multiplying that by my diameter of 0.667 feet, and then adding those up. Okay. So I got 186 feet of pipe, and the fittings themselves have a head loss that's equivalent to 118.6 feet. So I can add those together, I'll get 304.6 feet. We good with that? So find the equivalent length of the fittings, add that to the length of the pipe, you get the total equivalent length of that piping system that you're pushing the water through. So what do we get for the head loss?
4.85 times 3.04.
Yeah, you got to go 3.046 or whatever there, times the head loss per 100, which is 4.85. It's 14.77 feet. So your TDH then, you got to lift the water 36 feet, but you also have to overcome 14.77 feet of head loss. $50.77 feet. That's what that pump is going to have to do. So I don't know, what kind of pressure is that pump going to have to develop to push that water through that system?
The second last thing, it says total loss of pipe, or I'm sorry, head loss of pipe plus all fittings.
Oh,
What does that one give you?
that's the 4.85 times the 3.046. That's the head loss.
Because it
of
says
everything.
plus. Okay, I'm sorry.
Well, yeah, I might have a typo in there, I don't know.
Nope, I was just making
Is it
sure
okay?
it wasn't a number. Head loss of pipe plus. That's not actually plus, it's just kind of like and.
Yeah.
Okay.
Okay. So I'm getting about 22 psi that pump has to develop. That's what it's going to take to push that water through that system. This times 0.433. Right? And this is how we start sizing pumps. We get this number figured out. So now you know you need a pump that'll create 50.77 feet of head and also push 1,300 gallons per minute. So once you have that, you can start looking for a pump that can do that job. Okay. All right. So we've got that chapter 11 stuff that's due today. We've got the chapter 12 and 13 stuff due Wednesday. I'll get you a test review on Wednesday. Okay. All right. There we go.